Download this code from codegive.com, link in the description below. OK, let's delve into Newton's method for optimization. I'll provide a detailed, visually oriented explanation with code examples to solidify your understanding. Newton's method for optimization, a comprehensive guide. 1. Introduction, the problem and the goal. In optimization, our core objective is to find the minimum, or maximum, of a function. We're often dealing with functions that represent costs, errors, energy, or some other metric we want to minimize. Finding the sweet spot where the function reaches its lowest value is the goal. Newton's method is a powerful iterative technique to achieve this. 2. The intuition behind Newton's method. Newton's method is built upon a clever idea: use local information about the function to approximate it and then jump to the minimum of that approximation. Think of it like this. You're on a hill. Imagine you're standing on a hill in the dark, and you want to reach the valley at the bottom. You can feel the slope. You can feel the slope of the ground at your feet, the gradient. You can feel how the slope changes. You can also feel how the slope is changing, the curvature. Newton's method's approach. Instead of blindly taking steps downhill, you use both the slope and the curvature to estimate where the bottom of the hill should be if the hill was a nice, smooth parabola, quadratic curve. Then, you take a jump to that estimated location. You repeat this process until you reach the bottom, or get close enough. 3. Mathematical formulation. Let's formalize this with math. We want to find the value of x that minimizes a function f, x. Taylor series approximation. The core of Newton's method relies on the Taylor series expansion of f, x, around a point x_k. The second-order Taylor approximation is where f, x_k, is the first derivative, gradient, of f, x, at x_k. F, x_k, is the second derivative, Hessian, of f, x, at x_k. Note, for a single variable function, the Hessian is just a single number, the second derivative. Finding the minimum of the approximation. We want to minimize this quadratic approximation. To do this, we take the derivative of the approximation with respect to x and set it to 0. This simplifies to the Newton's method update rule. Solving for x gives us the update rule. This means, our next guess, x_k plus 1, is. In other words, we move from our current point, x_k, by an amount proportional to the negative of the gradient, scaled by the inverse of the Hessian. The Hessian tells us about the curvature. 4. Multivariate case, functions of multiple variables. The above formulation is for functions of a single variable. Let's generalize it to functions of multiple variables, f, x, where x is a vector. Gradient. The gradient, denoted as f, x, is a vector of partial derivatives. Hessian. The Hessian, denoted as h, x, is a matrix of second-order partial derivatives. Multivariate update rule. The update rule becomes where h, x_k, (-1) is the inverse of the Hessian matrix at x_k. 5. Algorithm steps. Here's the general algorithm for Newton's method. 1. Start with an initial guess. Choose an initial guess x_0. 2. Compute the gradient and Hessian. Evaluate the gradient f, x_k, and the Hessian h, x_k, at the current point x_k. 3. Solve for the update direction. Solve the linear system h, x_k, delta x_k equals -f, x underscore k, for delta x underscore k. This gives you the direction to move. In practice, you solve this system rather than explicitly computing the inverse of the Hessian. The solution delta x underscore k is the same as h, x underscore k, caret minus 1f, x underscore k. For update the solution asterisk update your current guess, x underscore k plus 1 equals x underscore k plus delta x underscore k. 5. Check for convergence asterisk check if the algorithm has converged. This can be done by checking if the magnitude of the gradient is small enough, f, x underscore k, tolerance, or if the change in x is small enough, x underscore k plus 1, x underscore k tolerance. 6. Repeat steps 2 to 5 until convergence is achieved or a maximum number of iterations is reached. 6. Code example, 1D function. Let's implement Newton's method for a single variable function using Python and NumPy. Explanation of the code asterisk. Asterisk f, x, asterisk defines the function we want to minimize. I've used a quartic function, x caret 4, for x caret 2 plus x. Asterisk df, x, asterisk defines the first derivative of f, x. Asterisk ddf, x, asterisk defines the second derivative of f, x. Asterisk Newton underscore method underscore 1D, x0, tolerance, max underscore iterations, asterisk this is the core function that implements Newton's method. Asterisk x0, the initial guess. Asterisk tolerance, the convergence criterion. We stop when the absolute value of the gradient is less than this. Asterisk max underscore iterations, a safeguard to prevent infinite loops. Asterisk the function iteratively updates x using the Newton's update rule. Asterisk it stores the history of x values in the history list for plotting. Asterisk plotting asterisk the code generates a plot showing the function f, x, the points visited during the iterations of Newton's method, and the final optimal point. This provides a visual understanding of how the algorithm converges. 7. Code example, 2D function. Explanation of the 2D code asterisk. Asterisk f, x, asterisk in this example, I've used the Rosenbrock function, a common test function for optimization algorithms. It's defined as 1, x0, 2 plus 100 asterisk, x1, x02, 2. It has a global minimum at 1, 1. Asterisk gradient, x, asterisk calculates the gradient of the Rosenbrock function. Asterisk Hessian, x, asterisk calculates the Hessian matrix of the Rosenbrock function. Asterisk Newton underscore method underscore 2D, x0, tolerance, max underscore iterations, asterisk the Newton's method implementation. Crucially, it now uses NumPy for vector/matrix operations. Asterisk np.linalg.solve, Hess, grad, asterisk this solves the linear system H asterisk delta underscore x equals grad for delta underscore x. It's numerically more stable than explicitly computing the inverse of the Hessian. Asterisk error handling is included by using try, except to manage cases where the Hessian becomes singular, non-invertible. Asterisk plotting asterisk the 2D example creates a 3D surface plot of the Rosenbrock function. The trajectory of the Newton's method iterations is overlaid on the surface, showing how the algorithm descends to the minimum. 8. Important considerations and potential problems. Asterisk initial guess asterisk Newton's method is sensitive to the initial guess. A poor initial guess can lead to divergence, the algorithm moving farther away from the minimum, or convergence to a local minimum, instead of the global minimum. Asterisk Hessian invertibility asterisk the Hessian matrix must be invertible. If the Hessian is singular, non-invertible, the algorithm will fail. This can happen if the function is not strictly convex. The code examples include error handling for this case. Local minima Newton's method can get stuck in local minima. This is a general problem for many optimization algorithms. Computational cost computing the Hessian and its inverse, or solving the linear system, can be computationally expensive, especially for high-dimensional problems. Modifications There are several modifications to Newton's method to improve its robustness and efficiency. Line search Instead of taking a full Newton step, x_k plus 1 equals x_k, h, x_k, caret minus 1f, x_k, a line search can be performed to find a better step size. This involves finding a value alpha such that f, x_k, alpha h, x_k, caret minus 1f, x_k, is minimized. Trust region methods These methods define a trust region around the current point where the quadratic approximation is believed to be accurate. The step is then constrained to stay within this trust region. Quasi-Newton methods These methods, example BFGS, DFP, approximate the Hessian or its inverse, reducing the computational cost of computing the exact Hessian. Learning rate Newton's method sometimes oversteps, especially when the Hessian is poorly conditioned. The learning rate alpha can be used to mitigate this issue by making sure x_k plus 1 equals x_k, alpha h, x_k, caret minus 1f, x_k, satisfies the Armijo condition, or the Wolf condition. 9. Advantages of Newton's method. Quadratic convergence near a local minimum, Newton's method typically exhibits quadratic convergence, which means the number of correct digits roughly doubles with each iteration. This makes it very fast compared to first-order methods, like gradient descent, once it's close to the solution. Scale invariance It is relatively scale invariant because it takes into account the curvature of the function. 10. Conclusion. Newton's method is a powerful tool for optimization, particularly when the function is well behaved, smooth, convex, and the Hessian is invertible. However, it's important to be aware of its limitations and potential problems. Understanding the algorithm's principles, its mathematical foundations, and the practical considerations for implementation will allow you to effectively use it in your optimization tasks. Remember to visualize the process, experiment with different functions and initial guesses, and consider using modifications like line search or quasi-Newton methods when necessary.